In this video, we'll be setting up the three-dimensional particle in a box problem. Note that the two-dimensional and the three-dimensional particle in a box problems can be set up following a similar pattern as the one-dimensional particle in a box. Assume we have a box such that the back corner of this box sits at the origin. X, Y, and Z are all three equal to 0. The box is of length A in the X direction, B in the Y direction, and C in the Z direction, such that the volume of the box is ABC. Inside the box, the potential energy is set to 0. However, outside the confines of the box, in all directions, the potential energy is set to infinity, trapping the free particle within the box. So we'll set up our Schrödinger equation, Hamiltonian operator acting on the wave function of our free particle equals the energy of that particle times the wave function. Recall that our Hamiltonian operator is always the sum of the kinetic energy operator and the potential energy operator. However, what is our potential energy that the free particle experiences inside the box or inside the system? Since this goes to 0, we know that our potential energy operator is also 0. We have no potential energy on the free particle. So our Hamiltonian is only equal to the kinetic energy operator. If we think back to our one-dimensional particle in a box, we defined the kinetic energy operator as negative h bar squared over 2 times the mass of the particle times the second derivative with respect to x, because the particle was moving only along the x dimension along the line. However, now we have a three-dimensional box, and so our particle can move in all 3 dimensions, x, y, and z. So we're going to have to take into consideration the second order derivative with respect to each dimension or each direction. So here we'll have negative h bar squared over 2 times the mass of the particle times the sum of the second partial derivative with respect to x, the second partial derivative with respect to y, and the second partial derivative with respect to z of our wave function. We also can set up our boundary conditions for this particle in a box. They're going to look very similar to the one-dimensional. Let's start with the x dimension. We know that when x is 0 and when x is a, at any other y and z values, the wave function must go to 0 because now we've exited the box. We can do the same thing in the y direction and say whenever y is 0 or y is b, the wave function must go to 0. And in the z direction, whenever z is 0 or z equals c, the whole wave function must go to 0 because, again, these are the boundaries of the box. We could use a similar separation of variables method to solve this now very complicated differential equation that we have in 3 dimensions with our Schrödinger equation. And we could say the main starting assumption is that our wave function psi could be written as some function of x times some function of y times some function of z, such that our 3 spatial dimensions could be separated into 3 functions. And if we did this, we'd see that for this function that only accounts for the x dimension would give us a cosine beta x plus b sine beta x. It's going to look just like our original classical wave and our one-dimensional particle in a box solution. And for y and z, we'd also get something like this. And because of our boundary conditions, our x of x function would go to some b sine n pi x over a. Similarly, we would see that y will follow the same trend, so the function for y would end up being some b2 sine n pi y over b, and z would give us some b3 sine n pi z over c.